Okay, folks, good morning. Any questions? All right. So we had our quiz number 4 last time, so let's go through the solution of the quiz real quick. So we had this boost converter. The current of the inductor is provided. Looking at the information, you can conclude that the minimum value of the current is 2 amps, the maximum value of the current is 4 amps, and the duty cycle is 25%. So part A is asking about sketch the waveform of the current passing through the diode, and we only have one diode, and obviously the current of the diode is always from its anode to its cathode. So we are looking for this current. In the first mode, the switch was on, the diode was reverse biased, therefore there was no current passing through the diode. So here we have 0. And in the second mode, the switch is turned off, therefore the entire inductor current passes through the diode. So we are just following that. All right, something like this. So this would be the current of the diode. The peak is 4. This minimum value is 2 amps. And obviously the duty cycle is 25%. So that was part A. Part B, find the average value of the current of the diode. So the average value of the signal is, we got to find the area of this trapezoid, then divided by T, the switching period. So generally you can write it this way. So instantly you can conclude that you don't really need to have the numerical value for the switching period. It cancels out. And if I plug in the numbers, Imax is 4, Imin is 2, division by 2 times 1 minus 0.25. So this would give us 2.25 amperes. So this is on average how much current passing through the diode. And now part C is asking about find the value of the output voltage. So we have discussed this before. On average, this current is 0. So on average, the entire diode current passes through the load. So the output voltage is basically the average value of the diode current multiplied by the value of the load resistance. And the load is given to be 4 ohms. So we are looking at an output voltage that is 9 volts. Okay? Then find the value of the input voltage. So we know, since this is the boost converter, this equation holds. And we have pretty much everything that we need other than the input voltage that we are trying to find. So 9 over Vn is 1 over 1 minus 0.25. Therefore, Vn is 6.75 volts. Okay. So instantly you have to double check. Okay, the input voltage is supposed to be less than the output voltage because this is the boost topology, and it is. And that's all that was asked. Now sometimes, especially at the earlier stages, we are, for instance, if you have a problem like this, I'm trying to kind of walk you through the ultimate goal. The ultimate goal is this: find the value of the input voltage. But I'm trying to give you some hints. For phase A, you should find the current of the diode, then find the output voltage, then find the input voltage. But sometimes, for instance, in your final exam, you may not see part A or B or C. All of a sudden, they ask you find the value of the input voltage. There's no walking through. There's just the ultimate thing that we want to find. All right. Any questions about the quiz? Okay.
voltage inductor current, like it is equal
Yeah,
to?
if you happen to have the equation, you can use that. This is assuming that you don't have that equation sheet, and this is 5 years later from now, and you don't even remember any of these equations. You just remember the very basics of, oh, by the way, on average, the current of the cap is 0. But yeah, if you have the equation, you can directly use that. Absolutely. All right, any other questions? Okay. So let's get back to our lecture. So we are still in chapter 7, which is called DC power supplies. The book has basically made a distinction between chapter 6, which is called the DC to DC converters. They are basically the non-isolated converters, to DC supplies that are kind of isolated converters. So the backbone of all of these topologies is some sort of a transformer with the primary winding and a secondary winding. Then we have more, elaborate, complicated models for transformers. We don't care about those. All we care about is the fact that our transformer has some magnetizing inductance. Most of the times we reflect this on the primary side. It doesn't matter. You can assume it's on the secondary side, or you can assume it's in both places. It doesn't really matter. So the first topology that we analyzed was the Flyback topology, and as you can see, it only has this transformer, one diode, one cap, and one switch. So the story is, when you turn the switch on, you are charging up this magnetizing inductance, and the current actually rises. When you open up the switch, this magnetizing inductance forces this diode to be on, and when this diode is on, the output voltage is applied across the secondary of the transformer. You can translate it to the primary side, and that voltage is negative. Therefore, the current of the magnetizing inductance ramps down, and you have more like a buck boost kind of a mechanism without that negative sign in some textbooks that appears. So your voltage transfer ratio is D over 1 minus D, which was the buck boost topology kind of a thing, plus obviously we have a transformer involved, therefore the turns ratio of the transformer is also appearing. This we did not cover this. This is the flyback converter operating under discontinuous conduction mode. It's very, very easy to follow. Then we started discussion on the forward converter. In the forward converter, we have 3 windings, and what's happening is when the switch is on, and by the way, this is the main inductor in the system, and this is the inductor we don't really need, but it's there, therefore we have to take care of it. So when you turn the switch on, this current ramps up as well as this current. They both get energized, both of the inductors. When we turn the switch off, 2 things are happening. One of them is this current that is non-zero now tries to go over here, and therefore it pushes this diode to be on, and that's a basically de-energizing mechanism for the magnetizing inductance. That's actually why we have D3 and the 3rd winding in the transformer. At the same time, similar to the buck topology, what's happening when the switch is open, we have a freewheeling mechanism over here through this diode number 2. And the way we design the system is we make sure that this guy operates under continuous conduction mode, but this guy is always de-energized before the next period starts. So that's what we did. That's what we did. We looked at some of the waveforms, some of the important waveforms, and we had actually a numerical example for this. This topology we did not discuss in our class. This is another forward topology, but as you can see, the transformer is a little bit simpler. It only has 1 primary and 1 secondary. But on the primary side, it's a little bit more elaborate. Instead of using only 1 diode and 1 switch, we are using 2 diodes and 2 switches. The principle of operation is exactly the same. When you turn, for instance, this switch on, you are energizing this inductor that you don't need. At the same time, you are energizing this inductor. Then you turn the other switch on, and what happens is you are having a current circulating over here on the secondary side, similar to the buck topology, but we are trying to de-energize the magnetizing inductance on the primary side. So this is in case you want your transformer to be very simple, And semiconductor devices are relatively cheap, so you can say I'm making my inductor a little bit simpler, but at the same time I am adding more switches and more diodes to the system. There are 3 more topologies that hopefully we are going to cover today. One of them is this guy, the push-pull topology, and then later the full bridge topology, and then later on the half bridge topology. What is common among all of these topologies is, if you look at the secondary side, they're almost the same. Like from this point to the right, they are basically the buck topology. All right, if you compare it with the buck, so the right-hand side of all of these topologies is very similar to the buck, and as it turns out, the voltage transfer ratio of these topologies, they're all actually like a buck-type converter. So they're all isolated buck topologies. And if you look at the circle that I have over here, if you go back to the rectification chapter, the very first topic that we covered, you can see you have like a kind of a center-tapped full bridge rectifier. So all of these topologies have a rectifier on the output side. Same story here. We have this full bridge center-tapped rectifier, full wave center-tapped rectifier, and again the same story over here. So as you can see, a trend appears in all of these topologies. So the trend is, using the switches on the primary side, you try to create some sort of a square-shaped signal applied to the primary windings, okay? And this signal, remember, we are talking about the transformer. On average, this signal should be 0. Otherwise, the transformer is going to get saturated. On average, there should be no DC bias for this signal, and there is no. So actually, this is my 0 level. So using the switching manipulation, you are creating this kind of AC signal. So you are from a DC source. Using the switches, you are generating an AC signal. Then on the output side, you rectify that AC signal that you have generated. So if you look at this voltage over here, Vx, it will be the same as this voltage, only a rectified version of that. And if you look at the Vx for the buck topology, is exactly the same thing. And then we are kind of having a low-pass filter to extract the DC component of these signals. So these topologies are basically all the same. Even for the forward topology, you can argue that we are almost doing the same thing. We are generating, and if you actually look at this voltage over here, on average, it should be 0. Okay, we are generating kind of an AC signal. On average, it's 0. Then if you look at Vx, it's kind of the rectified version of that. All right. So last time when we finished the lecture, we were in the middle of an example for the forward topology. So let's get to that example. All right. So the example was a design example, and we had this forward topology with an input voltage of 100 volts and output voltage of 170 volts, and we have been asked to, for instance, find the number of, the duty cycle and the number of turns for N1, N2, and N3 basically. The equations that we have to keep in mind is, one of them is the voltage transfer ratio, which is V out over Vn is N2 over N1 times D. So this is an important thing. And the other one was the condition that we had to satisfy to make sure that the magnetizing inductance is de-energized, which was this one. So we had like a rough design, and that was first selecting the number for N2 over N1. And for instance, here I chose N2 over N1 to be 2. And once I have this guy to be 2, and I have the input voltage level and the output voltage level, so I can find the duty cycle. Turns out to be 85%. Now that I have the duty cycle, I can look at over here and see what is the right value for N3 over N1, and you can select it to be 0.1. Now, so far, we are actually following these two equations, but the problem is, if you look at the switching, the voltage stress across your switch. In the first mode, the switch is on, so 0. Then there is a mode 2, the de-energizing mechanism going on, and then ultimately like this. So you can see that we have a relatively large stress on the switch, and that is 1 plus N1 over N3 times Vn. So now if you plug the numbers, N1 over N3 is 10, and the input voltage is 100, so the switch, when it is off, based on our design, should be able to tolerate 1100 volts, excuse me, which is relatively high. And let's say you went to the market and you were not either be able to find a switch like this, or it was too expensive, or as it turns out, the switches that are designed for high voltages, they have a very high conduction losses, and efficiency is important to you. And then you come back and say, oh, like part C is actually talking about that. Is it possible to reduce this stress on the switch? So let's say you're happy with a stress of 250 volts. You found a switch that is cheap or doesn't have a lot of conduction losses and can handle 250 volts. Now you want to go back and redesign your system again. So now we know that the maximum voltage that should be applied to our switch instead of 1100 volts should be 250 volts, okay? So now I know that 1 plus N1 over N3 times Vn, so this is the maximum voltage applied across the switch, should be less than 250. Okay, I have the value of the input voltage, which is 100 volts. So this gives me a hint that I should choose N1 over N3 to be smaller than 1.5. Now I choose it to be 1, for instance. So let's choose all right, so this is our first selection, and 1 over N3 should be 1. Now, going back, I have these equations. One of them was d times 1 plus N3 over N1 should be less than 1. And this is the condition that makes sure that the magnetizing inductance is totally de-energized by the end of the period. All right, so I've already selected a value for this, which is 1. So this gives me a hint about where to select the duty cycle. So if I follow this, this gives me that the duty cycle should be chosen to be less than 0.5. So let's say you choose 0.4. All right, let me just see if I can create some space here. All right. All right, so you choose the duty cycle to be 0.4. Now the last thing that you have to find is N2 over N1. And remember this expression, V out over Vn is N2 over N1 times the duty cycle. We have already selected the duty cycle. We know the value of the output voltage. We know the value of the input voltage. Therefore, this gives us N2 over N1 to be 4.25. So these two designs pretty much give you the same output voltage. However, the second one would actually apply a less stress on your switch. Now the bad news is I only focused on the switch. I didn't, for instance, focus on the diodes and stuff like that. But if you do so, you realize that if you're trying to fix a problem one place, you're going to add more problems somewhere else. So that's the trade-offs that you have to make in the design procedure. I just wanted you guys to be aware of that. All right, so let's go to our new file. All right, any questions? So this was all about the forward topology. We are moving on to the next topology, which is the push-pull topology. As you can see, it's a little bit more complicated. Let me see if I have a cleaner cleaner diagram over here that I can actually use. Yeah, here it is. All right. So what's happening in this topology is we have the primary side winding is actually center tapped, and also the secondary side winding is center tapped. Okay, by center tapped I mean if I have N1 representing, or N2 representing the number of turns over here, and N1 representing the number of turns over here, N1 is exactly the same as N2. Or let me do it, okay, let me use different notations. Number of turns for primary number 1, number of turns for primary number 2. They are the same. So it's this, we have access to the center of the primary side of the transformer. Also, same story here. Number of turns for secondary number 2 and number of turns for secondary number 1, they are the same. So pretty much everything is symmetric. Now what is N? So basically N, or I don't know, N secondary over N primary is defined to be N secondary 1 over N primary 1, or secondary 2 over primary 2, whatever. This is how it's designed. Or the total number of turns on the secondary side divided by the total number of turns on the primary side. They are basically all proportional with each other. So these are the things that we have to consider. We have two switches, switch number 1 and switch number 2. Since we are using S as the secondary kind of index, and now we are using SW for the switches. So SWs are actually appearing over here. All right. Now that we have two switches, we have to talk about the switching pattern. So what is our switching strategy? So this is our switching strategy. Okay. First of all, we divide the period into two equally, time spans, and we turn SW on in the first one. So this is for SW1. And then keep it off for the rest of the period. Now when it comes to the second switch, we do the exact same thing with a 180 degrees of phase shift. So something like this. So the commands that are generating or applying to switch number 1 and switch number 2 are exactly the same. They are just only 180 degrees out of phase from each other. And we have to define the duty cycle. And this is what I label to be dt. So the duty cycle is defined to be on time of S1 over the entire period. Okay. And as you can see over here, duty cycle is defined in a way that it is always obviously positive and less than 0.5. Okay. Now, in some textbooks, they are defining the duty cycle in a different way. They say duty cycle is the on time of the switch number 1 and the on time of switch number 2 over T. And that duty cycle can go all the way from 0 to 100%. And the way that we are defining the duty cycle over here, there is a 2 appearing in our voltage transfer ratio. There is a 2 appearing over here. And this is because of this, the way we have designed or defined the duty cycle, that the maximum value of the duty cycle is only 0.5. So if you open another textbook and you see this 2 is not there, no problem. The only difference is duty cycle has been defined differently. All right. So As you can see, you can identify 4 operating modes in the system. One mode is switch number 1 is on and the other switch is off. So we call it mode number 1. All right. Then the other mode is both of the switches are off. Mode number 2. Then there's a third mode during which switch number 2 is on and the other switch is off. So this would be our mode number 3. And then there's a fourth mode, which is actually exactly the same as mode number 2, because during this mode, again, both of the switches are off. So I just labeled it mode number 4, which is the same as mode number 2, basically. All right, so basically we have 3 modes. And as it turns out, in this topology, as you can see over here, we have not considered that there is a magnetizing inductance over here. All right? You can do the analysis with this magnetizing inductance. You can do the analysis without this magnetizing inductance. And as it turns out, because we are doing everything symmetrically, we don't really have to worry about this magnetizing inductance, and it is never going to get saturated. So in order to make things basically simpler, we assume that this magnetizing inductance does not exist. But in the end, we have to make sure that the voltage that we are applying over here does not have any DC bias, or in other words, it's on average, it's 0. If we satisfy that condition, the fact that we have neglected the magnetizing inductance doesn't really hurt us, and it is never going to get saturated. All right. So let's look at the first mode. So in the first mode, what's happening is we have turned the switch on. All right. And what's happening now is, as you can see, we are applying the input voltage across the primary side. So basically, we are actually closing this loop. All right. So we are applying the input voltage across the primary number 1, basically. All right. Switch number 2 is open or off. So now we have to figure out what happens to the diodes, diode number 1 and diode number 2. So remember, we are bring back that the rectifier mentality. Let me erase this a little bit. So if the primary side voltage is positive, that means this voltage is also positive, and this voltage is also positive. Now, going back to those rectifier circuits that we studied earlier, this is a center tap full bridge rectifier. When VS2, which is equal to VS1, they are always positive. During the time that they are positive, D1 is the diode that is on. Okay? So we are kind of rectifying this square-shaped signal, and D1 is on. So switch 1 is on, switch 2 is off, and D1 is on, and D2 is off. Okay, so everything is positive. Switch 1 is on, and D1 is on. All right. So if you write the equations, ultimately what we want to do is we want to find this voltage, which is labeled to be Vx, because Vx minus Vout is VL. And if you look at the average value of VL, you can find the voltage transfer ratio in the system. All right, so that's why we are trying to find Vx in this mode. So it's very easy. You can see in this particular mode, I don't want to get away from this figure. So basically in this mode, what we have is V primary 1 is Vn. So V secondary 1 will be Ns secondary voltage over Np O times Vn. Okay, so we have the V secondary 1 voltage, which is, because diode number 1 is on, V secondary 2. So we have this voltage, and because diode number 1 is on, Vs2 and Vx are the same, so this is also Vx. All right. So this is it's easy to find Vx. All right. And if you are interested in finding VL, voltage drop across the inductor is Vx minus Vout. So we are looking at Ns over Np times Vn minus Vout. And this is labeled to be equation number 1 because later on we are going to use it. All right, so this is all about mode number 1. Kind of like the Bach topology. If you turn the switch on, you will have some sort of a positive voltage over here which reverse biases the diode and everything works out. All right. Now, mode number 2. In mode number 2, which is basically this time span, as you can see, both of the switches are open, okay? So you can look at this equation. Okay, let me now erase this a little bit. So if you look at the schematic, if I keep both of the switches open, that means there is no way for this current to be non-zero because it has to go through the switch and the switch is open. And also, there is no way for this current to be non-zero because this is again the current of the switch over here, and because the switch is open, this current is 0. All right. So going back to so we are in mode number 2. I'm trying to figure out what happens to the diodes in this mode, basically. So we already know that okay. Number of turns of the first primary winding times the current of the first primary winding plus number of turns of the second primary winding times the current of the second primary winding plus number of turns of the first secondary winding times the current of the secondary winding plus oops. So this is a general equation holds for a transformer that has 4 windings in it, okay? So I just argue that because the first switch is off, this is 0. The second switch is off, this is 0, all right? So either you can conclude IS1 and IS2 they should be both 0, or they should be equal to each other with different polarities, okay? Now, if you look at the schematic, it is not possible for these currents to be both 0. Why? Because if this current is 0 and this current is 0, okay, look at this current. It flows over here. That means if you apply KCL over here, this current should also be 0. And this is the current of the inductor. It was being energized in the previous mode, and it is non-zero. So the inductor forces IS1 and IS2 to be non-zero. So I of the current of the inductor is not 0. Therefore, IS1 and IS2 they cannot be both 0 at the same time. So combining these two equations, one of them is saying that NS1 times IS1, NS2 times IS2 should be 0. And by the way, NS1 and IS2 are the same. So technically, this is telling me that IS1 plus IS2 should be 0. The second equation tells me because we have that inductor on the output side, both of these currents cannot be 0 at the same time. So the conclusion is IS1 is the opposite of IS2 is half of the inductor current. Alright, so this is something that we haven't seen before. When we open up both of the switches, both of these diodes are on, and each one of these diodes is handling half of the output current. So if this is IL over here, I have half of that current over here, and then half of that over here. And it both satisfies KCL over here, and also satisfies this equation that holds for our transformer that N1 I1 plus N2 I2 plus N3 I3 plus N4 4 should be 0. Because as you can see, one of these currents is coming out of the dotted node, the other one is going into the dotted node. So it's actually making everybody happy. All right, so this is what's happening. When both of the switches are off, both D1 and D2 are on. All right, now if you look, okay, if D1 and D2 are both on, I have a short circuit here, I have a short circuit here. If I apply KVL to this loop, what I conclude is, okay, VS1 minus VS2, oops, no, if you apply KVL, gives you, okay, KVL gives you VS1 plus VS2 should be 0. That's just the KVL in that loop that we have two diodes on. So basically I'm looking at this loop over here, writing in KVL, okay? The other equation that I have for any transformer is, remember, I assume the number of turns over here are the same. That means VS1 is always the same as VS2. Okay, so we have two signals, they are identical with each other, and if you add them with each other, it's 0. That means each one of them is 0. So the other one is VS1 is the same as VS2. So looking at both of these gives you VS1, VS2 is 0. So on the secondary side of the transformer, I have more like 0 voltage applied over there, or basically like a short circuit. As soon as I have this, I can translate it to the primary side and also conclude V primary number 1, which is the same as V primary number 2, should also be 0. Just multiply by the number of turns, which doesn't matter. 0 multiplied by anything gives you 0. All right? All right. So this is how you translate the voltage to the primary side. So technically, what we are talking about here is in this particular mode, mode number 2, which is a strange one. From here to here, I have 0 volts, and from here to here, we have 0 volts. Okay, so 0 volts here, 0 volts here. So if we apply, for instance, KVL over here, you can see how much voltage is applied across your switch in this mode that is off. Okay, so for instance, V switch number 1 will be the same as Vn. And that is actually the same as switch number 2. So in this mode, both of these switches are supposed to handle the input voltage in terms of the voltage stress, because the transformer is like shorted, basically. All right, so this was all about mode number 2. The only thing that we have to take care of is, remember, in the end, we are trying to track Vx. Okay. So I want to see how much Vx is in this mode. I just argued that from here to here I have 0 volts. This diode is on. So if you apply KVL to this little loop, Vx is also 0. All right. Therefore, Vx is 0. And this turns out to be equation number 1. In the first mode, we had an expression for Vx. In the second mode, now we have an expression for Vx. Now let's take a look at the third mode. Are there any questions so far? So it's quite simple. You turn switch number 1 on, you are energizing this inductor. You turn both of the switches off, nothing is going on. We basically are applying 0 volts over here, and we are actually providing a freewheeling, kind of a mechanism going on the output side. All right, now let's look at the third mode, during which we turned this switch on, switch number 2. Things are almost the same with the polarity of negative, a negative sign actually involved. So let me raise this a little bit, or maybe I should. Let me get another new figure. So we are analyzing mode 3. S2 is 1. Okay, let me write it SW. And the first switch is off. So technically we are focusing on this region over here. All right? Okay, so let's take a look. So I have this switch shorted. Now, if you apply KVL around this kind of a twisted loop, what you can see is V primary 2 is the opposite of Vn. So now we are applying a negative voltage to the primary side of the transformer. And first of all, remember V primary 2 and V primary 1, they are always the same because the number of turns are the same, okay? Because of this equation that I wrote earlier, because of this, V primary 1 is always the same as V primary 2, okay? All right, so we are applying a negative voltage across the transformer. This negative voltage translates to the secondary side. So if you look at V secondary 1, which is the same as V secondary 2, is negative N secondary over N primary times Vn. Okay. So again, going back to our rectifiers, we have a rectifier system, a center tap full wave rectifier. Now as it turns out, our voltage is negative, and if you remember, if the voltage was negative, D2 was the diode that was conducting. Okay, so we don't do that analysis anymore. I'm just refreshing your memory. Because this is negative, therefore D2 is on and D1 is off. Okay. So remember, when the secondary voltage is positive, D1 is the one that is on. When it is negative, D2 is the one that is on. Okay, so D2 is on. So now that D2 is on, what you can do is you can now basically write Vx. Okay. So if D2 is on, if you look at, I don't know, it doesn't look like a loop, but it is a loop actually. Okay, let's just start from here. Go through here. So VS1, we have shorted. Go through here, Vx, and come back. Go, okay. You go here and then come back, basically. It's like a little weird looking loop. So what you can say is Vx that we are interested in finding is the opposite of Vs1. And because Vs1 is already negative, therefore Vx is positive, and it is Ns over Np times Vn. And that's the rectification job that we expected. If the input voltage is positive, the output of this rectifier, which is Vx, is positive. If the input voltage is negative, again, the output is still positive. Okay, that's what I mean, positive here. All right. And now we have Vx. Now you can find VL, which is Vx minus Vout. And by the way, by VL, it's already labeled here. This is our VL. VL is Vx minus Vout. So this is actually the same as what we had in the first mode. All right, so this is equation number 3. And if you compare it with equation number 1, they are basically the same. Okay, here's the equation that we had for the first mode. So from the standpoint of the output circuit, the first mode and the third mode are basically the same. Both of them are providing a Vx that is positive, and it is actually energizing the inductor. All right. So this was all about mode 3. Now before I move on to mode 4, let me just look at the voltage drop across the switch that is off. I want to see how much voltage appears across the switch, because ultimately I have to purchase a switch to be able that can handle this voltage stress. So we just argue that, all right, VP1 in this mode is negative VN. All right, here it is. VP1, which is the same as VP2, they are both negative VN because switch number 2 is closed. Now, if you apply KVL to this loop, you're going to realize that the voltage stress on your switch is twice Vn. So voltage stress on the switch, this particular case switch number 1, is twice the, positive, twice the input voltage. All right? All right. So this was all about mode number 3. And mode number 4 is exactly the same as mode number 2. Mode number 4 is exactly the same as mode number 2. So technically in that mode, both of the switches are open. There's nothing going on the primary side. On the secondary side, both of the diodes are on, and each one of them is conducting half of the current of the inductor current, and Vx is 0. So we are kind of like the Bach topology. We are applying 0 to the left side of the inductor. Therefore, the inductor is going to get de-energized. So Vx is 0. All right. Now that we have looked at all 4 modes, we want to look at the average value of, or basically VL. We want to look at the average value of the inductor voltage to be able to find the voltage transfer ratio. So let me draw it. Actually, I have it over here. Let me just repeat it. All right. So in the first mode, so we are drawing VL, voltage drop across the inductor. In the first mode, switch number 1 was on, and the source voltage was translated to the secondary side, and VL is basically this expression. N secondary over N primary times the input voltage minus V out. All right, so this is what's happening in the first mode. In the second mode, both of the switches were off, both of the diodes were on, Vx was 0, so we are applying a negative voltage to the inductor, kind of like the Bach topology. And this third mode is exactly the same as this first mode as far as VL is concerned. We just wrote the equation over here. Equation number 3, Ns over Np times Vn minus V out. So I'm just going to draw it over here. And the fourth mode is exactly the same as the second mode. So if you look at VL, it's like a square-shaped signal. Sometimes it's positive, sometimes it's negative, but on average it should be 0. So the average value of VL should be 0, or you can write it in this form. Or basically this area should be the same as this area. Or in the end, you are going to end up having a voltage transfer ratio, which is something like this. So there's a 2 appearing here because of the way we have defined the duty cycle. Our duty cycle, the way it has been defined, can go from 0 all the way up to 50%. And there is Ns over Np appearing here because we are having a transformer. So in all of these isolated topologies in the voltage transfer ratio, you would see this Ns over Np. And also D appears, kind of like the Bach topology. So if you look at the Bach, and you can see basically they are the same. So the the push-pull converter is kind of like basically a Bach converter, an isolated Bach converter. Now there are differences over here. One major difference is obviously we are using a transformer. The other major difference is here we are using, on the input side, we are using 2 switches, and on the output side, we are using 2 diodes. This is kind of an indication that the stress, especially the current stress, is divided between the 2 switches. So this converter potentially can handle higher amounts of power. For instance, if you have a buck converter that can, for instance, handle 100 watts, but if you wanted, for instance, develop a converter that has the same functionality of the buck, but should be able to process 500 watts, you realize 500 watts of power gives you a lot of current stress on your switches. Forward topology may be a better topology because the current stress is a split between 2 switches. So they are kind of shouldering the load, basically 2 switches. So this forward topology would be a better option, better choice for power ratings beyond maybe 200 watts, 300 watts, all the way to, for instance, 1 kilowatt or something like that. So that's another difference. All right, so let's look at a few of other waveforms. For instance, well, first of all, we are actually defining, I have done this already, our switching pattern here. It's very important to note that this is half of our cycle. All right. So we were looking at Vx. In the first mode, Vx is a reflection of the input voltage, Ns over Np times Vn. In the second mode, because both of the diodes were off, Vx is 0. In the third mode, Vx was the same as the first mode, Ns over Np, because we have a rectifier, and then the fourth mode, it was 0. If you look at the inductor current, in the first mode it rises, in the second mode it falls. In the third mode it rises, and in the fourth mode it falls. And if whatever switching frequency we have, let's say this is 1 over our switching frequency, you can see the ripple that appears in our inductor is twice. The frequency of the ripple is twice as much as our switching frequency, which is a good thing actually. Looking at the voltage stress of the switch, like let's say switch number 1. In the first mode, this switch was on, so 0 volts. In the second mode, remember in the second mode we had it over here. Voltage on the switch is the same as Vn. Why? Because we didn't have any voltage over here. This was basically 0, and therefore Vn applies across the switch. So we had Vn over here, and the second mode and the fourth mode are the same, so the same appears here. In the third mode, when this switch was off and the other switch was on, and we looked at it over here, and we realized that twice the input voltage appears across this switch. So it looks like this. So this level is 2 Vn, and this level is Vn. So if our input voltage is 20 volts, we should have a switch that can handle twice that, 40 volts, which could be considered a disadvantage of this topology. The stress on the switches, the voltage stress on the switches is twice as much as the input voltage. Now, as far as we are talking about voltage stress on the components, let's look at, for instance, voltage stress on this diode over here. All right, remember this diode was on in the first mode. Okay, so it was on, no voltage stress. And both of the diodes are on in the second and the fourth modes. So I have again 0 here and 0 here. The only time that this diode is off is during this last mode that we analyzed, the third mode basically. And you can actually apply KVL around this loop to find the voltage drop across this diode that is off, because D2 is on, so VD1 is twice basically VS1. And remember, VS1 is negative, makes sense, so we have a negative voltage applied across this diode. So we have twice VS1 which is negative 2 times something like this. Okay, so another indication when it comes to selecting this diode, you know how much voltage stress is actually applied here. Now I'm not going to draw the current waveforms. Maybe I should, maybe I shouldn't. If I don't, then I can actually use that in a quiz problem. Let me just do it. So let's say we are trying to find the current waveform of switch number 1. So the switch color, there's a little bit. So let's say this is the current waveform in continuous conduction mode for the inductor. All right, and now we are trying to plot the current of the first switch. Remember, the current of the first switch is non-zero only in the first mode. The second mode, the switch was off, so I know this is 0. In the third mode, the switch was also off, so no current, and also in the fourth mode. So this part was very easy, it's just 0. In the first mode, however, it is proportional with the current of the inductor, but remember the current of the inductor in the secondary side, we have to translate it to the primary side. Also, if this is I max, this will be I max over n primary times n secondary. And the same thing for here. If this is I min, so this is the current waveform for our first switch. Now, let's say you also are curious about the current waveform for this diode, ID1. All right, so let's plot that. All right, so let me kind of superimpose that. So let's say we already have IL. So it's something like this, and from this IL I'm trying to plot the current of the diode. First of all, we just analyzed this. In the third mode, this diode was off, so no current in the third mode. All right. In the first mode, D1 was the one that is on, and it was actually conducting the inductor current, so it's actually following this. In the second and fourth modes, the diode current was half of the inductor current. So whatever I have to just divide it by half. So this is the current waveform we are looking at. So this peak is I max over 2. And this is also I min over 2. All right. So this was for the first diode, and then you can do the same thing for the second diode. All right. Any questions? All right. So let's move on. We have 2 more topologies left. We are going to go through these 2 very, very quick. Oh, before we do that, remember I said that I'm neglecting the magnetizing inductance. All I have to do at the end is make sure that the voltage that we are applying across any of these windings, because they are proportional with each other, I just have to consider one of them and make sure on average this voltage is 0. So let me actually plot that. Let's plot VP1. In the first mode, the switch was on, and VP1 and VN were the same. In the second mode, on the secondary side, both of the diodes were on, So V secondary 1 and V secondary 2 were both 0, and therefore V primary 1 and V primary 2 are both 0. So this is 0, and also this is 0. All right. In the third mode, the second switch was on. V secondary 1 was negative V in, which is the same as V primary 2 was the negative of V in, which is the same as V primary 1. So we had negative V in over here. Use black now. All right. So as you can see, it's a symmetric voltage waveform. So ideally, we should not worry about the magnetizing inductance. Lm, that we did not even consider in this analysis, does not get saturated. The reason is, on average, this voltage is 0. So as long as everything is ideal and we do everything exactly symmetrically, there is no worries about this magnetizing inductance to get saturated. But in practice, there are, because we cannot, no matter how hard you try, you cannot do things exactly symmetrically. Or, for instance, the first switch and the second switch are not exactly the same in terms of their characteristics. One of them has a little bit of a larger internal resistance. Or, for instance, the number of turns, I just assume that we are exactly having access to the center of this winding. Maybe you don't, for instance. And one is 50 turns, and then two is 49.5 turns, something like that. In practice, the push-pull converter has these problems that if you don't really do things exactly symmetric, you are actually forcing your magnetizing inductance to get saturated. There are lots of papers and solutions to avoid that. So just remember, if you build a push-pull converter, the first try that you make, it's definitely going to saturate it and not work. But if you apply some of those tricks, you can actually make sure that things are symmetric and you're not really violating anything. All right, so this was all about the push-pull topology. So you will see at least hundreds or if not thousands of papers just focusing on the push-pull converter and trying to make sure the magnetizing inductance is not saturated. All right, so there's lots of papers out there. Okay, now let's talk about full bridge converter. Let me see if I can move things down a little bit. Maybe I cannot. Maybe I shouldn't even try. Okay. So here is our full bridge converter. You can see on the output side, exactly the same as the push-pull. You have a center tap full wave rectifier cascaded with a low-pass LC filter, then ultimately a load. On the primary side, you only have one winding and 4 switches this time. And as it turns out, this does the exact same thing as the push-pull converter did, with 2 switches and a center tap winding on the primary side. All right, so let's take a look. And the way these switches are turned on and off are similar to the push-pull converter. So technically what I'm saying is, let me write it down here. Let me try and push these things down a little bit so they are aligned with each other. All right. Insert. Okay, so we have lots of space down here, although it's deleted now. Shift. Oops. Uh-oh, it's selecting that one as well. Okay, never mind. Never underestimate the stupidity of computers. All right, so let me go back. All right, so the switching pattern is, let me draw it down here. We are talking about a forward converter now. No, it's not forward, it's full bridge. All right, so we have 4 switches here, right? Switches 1, 2, 3, and 4. We turn 1 and 2 identical, switch 1 and switch 2. Kind of like what we did for switch number 1 in the push-pull converter. We divide our period to 2 equal 50% time intervals, and in the first one we turn switch 1 and 2 on for duty cycle times period, and then for the other 2 switches do the exact same thing with a 180 degrees of phase shift. So this is again dt. All right. I'm sorry, for 3 and 4, not 2 and 3. All right. So let's go back one more time and take a look, or I can steal it from here maybe. All right, this is what it is. Oops, what did I do? Control copy. All right, so look at this one and just consider that switching pattern that I just talked about. So one time I turn S1 on and S2 on together. So what happens is, if you look at this primary side voltage, it's the same as Vs. So I'm applying positive value of Vs or Vn to the primary side. And the loop is basically this loop. All right. Then the other mode, which is mode, for instance, 3, I turn S3 on and S4 on. And if you look at KVL now, to the primary side, we are applying negative Vn. So let's follow that. All right. So the input voltage comes through the switch, goes here, goes through this winding, goes here, and goes down. So we have like a twisted kind of a loop. And if you look, V primary is negative Vn. Kind of like what the trick that we were doing for the push-pull converter. I mean, one time you're applying a positive voltage, on the other time you're applying negative voltage, and then everything is symmetric. Now there are modes that all of 4 of these switches are off. So this would be mode 1. Oh, I did. Okay, let me do it with red. So this was mode 1. This one that I drew with blue was mode, let's call it 3. And then we have, I don't know, this to be mode number 2. And this is 4, which is exactly identical to 2. So in these 2 modes, 2 and 4, all of the switches are off. Kind of like the push-pull. Nothing is going on the primary side. Both D1 and D2 are conducting, and each one of them is handling 50% of the current of the inductor. All right. So if you look at this switching pattern that I drew up here, so if you look at V primary, okay, the primary side voltage, which is this voltage from here to here, okay? In the first mode, I just looked at it, it is Vn. In the second mode, it is 0 because both of the diodes on the output side are on, and that shorts the secondary loop, therefore everything is 0. In the third mode, it is negative Vn. And that's it. Again, like the push-pull topology, we are applying a square-shaped signal to the primary side of a transformer. On average, this signal is 0 because we are doing everything symmetrically, so we don't have to worry about the magnetizing inductance. And all is happening on the secondary side is we are just rectifying this voltage. So for instance, if you look at Vx over here, Vx is the rectified version of the signal multiplied by the turns ratio of the transformer. So if I just plot Vx, is the same thing, only rectified. So Vx is like the absolute value of V primary. Obviously, there is a turns ratio involved, N secondary over N primary. So this would be N secondary over N primary times Vn. All right, something like this, okay? Exactly the same as what we had for the push-pull converter. And when it comes to VL, remember VL is Vx minus Vout. The voltage drop across the inductor here is basically, I'm looking at this loop. Vx minus Vout is VL. So on average, Vout is almost a DC signal. The instantaneous value and average values are the same. On average, VL is 0. So my output voltage is actually the average value of Vx. Obviously, we are having a low-pass filter. It's only going to give us the average value of the signal. So if this signal that I have, if I just look at its average value, that is my Vout. And that would give you Vout is 2 N secondary over N primary times D. Something like this. So exactly like the push-pull converter, the only difference is on the primary side, instead of using two switches and 2 windings, we are using 1 winding and 4 switches. Okay? So this is the full bridge converter. So we kind of convert a DC signal to a symmetric, a square-shaped AC signal. We pass it through a transformer, then we rectify it, then we look at the low-pass, apply to a low-pass filter to actually obtain its DC value and apply that to the load. Now, you may argue that this converter is a little bit expensive because we have to pay for 4 switches. And obviously the reliability also comes in, and the gate drives and things like that. Then there is another way of doing that with only using 2 switches, which is called the half-bridge rectifier. And here is actually the topology. Again, the secondary side is exactly the same. A center tap, full-wave rectifier, a low-pass filter, and the load. On the primary side, we are eliminating the 2 of these switches and replacing them with 2 capacitors. So I think I'm going to talk about it next time, the half-bridge converter. But everything is pretty much the same. I mean, it's just a matter of convenience. Do we prefer to have capacitors in our system or switches in our system? So I'm going to stop here. The sign-on sheet is open.